This is how we implemented it, discretizing with a theta method once again. This is the weak form with theta method. And this is how the code looks like respect to the part of the heat equation. Once again, we have the linear form and the bilinear form obtained by the automatic derivation. This is the complete model, how it looks like in the UFL file. We have the definition of the finite elements. This, what we do then is use a mixed element, and this is the definition of the trial function, and we use a split, this possibility to split to highlight the different contribution, which is the displacement, the temperature, the concentration, and the chemical potential, which is all we need to set up completely the model. This is the definition we use for the DG implementation with the facet normal and mesh size. And those are some time-stepping parameters. We use a generalized alpha method, so theta A is can be different from theta U, and from theta B if we want also damping term in the balance of linear momentum, and from the parameters that we use for the evaluation of the Kine-Hillard equation at the midpoint and of the heat equation at the midpoint. This is the structure of all the files involved in the framework. These are 4 different UFL files with which we can switch and disregard one part of the model with respect to the other, because the model is pretty complex. So to study it at a preliminary stage, we need to maybe put away for a while some equations, and so going with only a part of the model. These are header files we use to specify what to pass what the UFL files require, and all these take definition of some classes from this file, model.h, this header file. We need also to provide some parameters for the problem, and also boundary condition and the initial conditions, which are absorbed by this header file. And then we got another header file to perform the updates of the velocity and of the acceleration. We take all this file and we feed it into the main file, from which we can switch between one model or another model. And this is a header file we use for defining, for a user-defined nonlinear problem. Okay, let's talk about some recent development in the code which allowed us to formulate the problem as we wish. Basically, I'm going to talk about 2 of them. The improvements in the quadrature representation, which allows us to remove what we did. It was a trick to implement fifth order polynomial, and then the use of the automatic derivation. Improvements in quadrature representation allowed us to remove this trick, because to evaluate the stress tensor we got, because it's a phase transition problem, we got a fifth order polynomial, and before the recent development we weren't able to compute it. In this way we had to define say side variable in the solution vector, which was E2, which is here, E2, so a mixed element, and to write obviously a weak formulation saying that this variable E2 is basically the function E2 we gave. In this way we were able to compile the form file. But obviously it's not a nice solution. Fortunately, recent development allowed us to remove this trick, and here you see that we evaluate the fifth order polynomial part of the stress tensor in the same way as we do for the other part, and so in this way we don't need this linear and this bilinear form, and also we can cut out this variable. The second thing I'm going to talk about is the automatic derivation. This is how the code looked like before the derivation, without using the automatic derivation with the bilinear form written by hand, which is a process that can be error prone. And this is how the code looks like. It's quite a massive improvement in the readability and in the length of the code. We removed all the definition of the bilinear form and we let it compute automatically by the code. And once again, this is a procedure which is less error prone. You can do error once you trust someone who coded that. And I'm going to finish with some conclusions. The model we have to deal with is rather complex because it's nonlinear. It has we have to deal with a high order polynomial, and we got fourth order terms. We got different kinds of equation, which requires a different approach for the Canning equation. We had simply a split in two equations. For the balance of linear momentum, we had to use a DG approach, and but the implementing it in Dolphin seems a good way, because we are pretty much close to feeding the system with the equation as we would write by hand on the paper. So especially with the recent development, and also the velocity in compiling the code allows us to do many tests, because it takes roughly 1 minute to compile the linear and the bilinear form. So we can disregard some part of the model, add them, make tests, and this speeds up the process of getting knowledge from the model. Last, one thing we have to account for in the next future is the fact that we want the two equations, the two evolution equations, the Canning and the balance of linear momentum, to evolve at different time scales, and so we need to think about some time adaptivity. We are thinking about that from very rough time adaptivity to some finer methods, but still it's we have to think about, because actually we don't have time adaptivity yet. Thank you.